it's really great to be in Trieste. It's beautiful. And since my abstract doesn't say that, this is a joint work with Jong-an Park and Masaki Taniguchi. Masaki is here, which is great because I'm not really a gauge theory expert. Okay, so today I'm here in order to announce the proof of the following theorem, which has been announced also by Masaki a few hours ago, that that basically every cable of the figure 8 knot has infinite concordance order. In particular, the proof that I'm going to present today is the even cable case, the general even cable case. So I'm going to announce the 2n comma cable of the figure 8 knot whenever n is non-zero is not smoothly sliced, and additionally it has infinite order, but it's not as important as being smoothly sliced, I think. Okay, so that's the theorem. This program was started by the proof of 2 on cable case, which was proven using very different method, namely involved Higger floor theory, and then being concluded right now. But let's start this talk with why is this problem so important. Basically, it is very important because it is linked to this slice ribbon conjecture. We say that a knot is smoothly sliced if it bounds a disk inside the 4-ball smoothly. And then weird thing about this detecting or whether you're not given knot is smoothly sliced or not sliced is that it is a very hard problem. It is incredibly hard. It is very hard to detect whether your random knot is sliced or not sliced. Of course, there are very easy cases. For example, if your knot has RF invariant 1 or irreducible Alexander polynomial, then obviously it's not sliced. But if you think if you start to think like your knot has a very good chance of actually being smoothly sliced, then the problem gets really, really difficult, because you have to draw one if it is actually sliced. Currently, this is the only way to prove that your knot is sliced. And drawing an explicit slice disk inside the 4-ball is obviously very difficult. So if you have a slice, any surface inside the 4-ball, smooth surface inside the 4-ball, the nice thing is that you can, since everything is smooth, you can do the Morse theory. So any surface will be decomposed into something like bird cobordism and then some saddle cobordisms. And then you can also have that. Something like this. So you can have birds cobordism, saddle cobordism, and then some death moves. And because of these death moves, you cannot in general easily draw your slice disk inside a 3-dimensional space, which is much easier. The idea is that if you don't have these death cobordisms inside your slice disk, then your knot is ribbon. And what happens is that you can just draw your knot as an immersed disk inside this 3-sphere instead of 4-ball by allowing these type of singularities here, which are called ribbon singularities. Whenever you see a ribbon singularity, you perturb one of the copies into the fourth coordinate. So whenever you draw these kind of things, you can automatically translate into embedding of a disk inside the 4-ball. And so they are ways to draw ribbon disk inside the 3-dimensional space. So by definition, ribbon knots are smoothly sliced. They're exactly the knots bounding a disk, which admits decomposition into birds and saddles, but no deaths. And then Ralph Fox asked in 1962 whether the converse is true. So ribbon knots are obviously smoothly sliced. So if you have a smoothly sliced knot, does it always bound a ribbon disk as well? And that is very non-trivial. Is widely open even for now. It's called the slice ribbon conjecture, and it is even more difficult because in the level of surfaces, then it is quite easy to come up with a smooth disk which cannot be smoothly isotoped to the ribbon position. There are many such a slice disk. So what this conjecture is saying is, if you're not bound some disk which might not be isotoped to a ribbon disk, then does it bound some other disk which is actually ribbon? That's why it's even more difficult. And in general, if you consider this generalization of this problem into general concordances rather than slice disk of knots, then there are pairs of knots which are concordant but not relayed by a ribbon concordances. So this conjecture is basically asking whether you have a very special things occurring when one of this is a knot. So and that's why I don't think this conjecture is really believable. Yeah, so I think it's false. I hope a lot of you agree. But there has been no counterexamples anyway. And then the story starts from a theorem of this Miyazaki, which was probably the first constructed potential counterexample to this slice ribbon conjecture. So to disprove this conjecture, you have two ways. You may come up with a knot which is not ribbon, but you don't know whether it's slice, and try to prove that it is slice. Or you can do the other route. You have something which is smoothly sliced, but you don't know whether it's ribbon, and you think it's not. There are families of potential counterexample in both directions, but the Miyazaki is the former one. So he constructed a sequence of knots which he could prove that they are never ribbon, but seems quite smoothly sliced enough. So here's his construction. You start with a knot which is negatively amphichiral and fibered, and also has irreducible Alexander polynomial. Then any even comma one cable of it none of them is going to be ribbon, but they look sliced enough. It is not a mathematical statement because it's just a speculation. But I think the reason is, since it's negatively amphichiral, the connected sum of two copies of it is smoothly sliced, and then like even comma one cable kind of looks like you're taking connected sum of even numbers of them. So philosophically, it looks quite sliced. And indeed, it is very hard to obstruct their non-sliceness. So anyway, from this Miyazaki's work, we have a family of potential counterexamples to slice ribbon conjecture. And if you can prove that any of them is smoothly sliced, then the conjecture is false. Let's look at the simplest case of this family of counterexamples. We have a lot of conditions here, so your knot has to be negatively amphichiral. It also has to be fibered. It also has to have irreducible Alexander polynomial. You have three conditions. But there's a very simple knot which satisfies all of them. It's figure 8 knot, which one of my favorite knots. So if you take this example, then well, it is fibered. It is even strongly negative amphichiral, and its Alexander polynomial is t minus 3 plus t inverse. It is irreducible. So the simplest case of this counterexample is the 2-1 cable of the figure 8, and then you're asking whether it is smoothly sliced. Interestingly, this particular problem that whether 2-1 cable of figure 8 is sliced goes even further back than the Miyazaki's work. It goes back to Kawauchi's unpublished note in 1980. Okay, so let's briefly discuss about why this question was very difficult. Obviously, it was difficult because they are not sliced, but but obstructing the sliceness was also difficult because not many obstructions work here. There are three big ones, big properties. So first of all, it is. Sorry. Yeah. Oh yeah. Sorry. It's next slide. Sorry. Anyway. Yeah, so here are our works regarding the smooth sliceness of even cables of figure 8. So we first proved that this simplest case, the 2-1 cable case, is smoothly sliced and has infinite concordance order using involtive Heeger floor homology with Irving Dai, Abhishek Malik, John Park, and Matt Sofrigan. And the nice thing about this work was that you can easily replace 4-1 with very, very general family of negative geometric chiral knots. In order to work over higher even cables, we had to stick to the figure 8 knot. We lose a lot of flexibility. But anyway, by sticking to the figure 8 knot case using something called the real Froishoff invariants and their cobordism inequalities, we were able to show last year that this is not smoothly sliced. At that point, we didn't know whether it had infinite concordance order. But finally, by using real 10/8 inequality, we were able to show that every even cable are not smoothly sliced and also have infinite concordance order. And let me just note that if you ask about what happens for odd cables, they are linearly independent. The non-sliceness itself is very easy for odd cables because our ARF invariant is 1. But even before our work, the fact that their infinite concordance order was even not known, and that was the first example of a rational slice knots which has infinite concordance order in 2020. Okay, so yeah, back to this, why this problem is very difficult. So first of all, it is algebraically sliced. It is zero in the algebraic concordance group because we're taking even cable, and that it kills almost all of the topological invariants. Then it bounds no homologous disk inside both CP2 and minus CP2, and that's just because the 4-1 itself, the figure 8 knot itself, bounds such a disk inside CP2 and minus CP2. You just cable your disk, and because of that, using the work of Manolescu, Sarkar, Willis, and Marangan, it implies that S is 0. So you cannot use S invariant for obstructing those things. And finally, they are rationally sliced. And most of the floor theoretic obstructions are rational concordance obstructions, such as like tau invariant and those stuffs. And that's because the figure 8 is a strongly negative amphichiral knot. So that means there's a orientation reversing involution of R3, which fixes your knot pointwise. You cannot easily see from this diagram because it's not drawn in that symmetric way. But if you draw it something like this, then now you can see by reflecting along the origin, you see that now you're not as symmetric with respect to this orientation reversing involution. And if you have such a knot, Kawauchi proved that those knots are always rationally sliced. So his construction is that if you have such a strongly negative amphichiral knot, and you denote the orientation flipping involution by tau, then if you take the zero surgery and the induced action of tau, now this is a free action. So what you do is you take a zero trace of this knot, and then you identify the points on the boundary using this free involution. That gives you a rational homologous force sphere in which K is sliced. Yeah, so that's why they are so difficult. And then interesting fact is that these look all different, but Adam Levine proved that they're actually all diffeomorphic. So you can draw his Kirby diagram very easily. He calls it a snack. I think it comes from S and a K, and then he just adds C, and Keegan Boyle first called it snack. So it kind of looks yummy. But then the choice of C is quite arbitrary. So I think you might also call it a snake. Yeah, anyway. So how do we deal with this 2-1 cable case? In our paper with Dai, Malik, Hom, and Stoffrigen, we started by taking its branch double cover. So if you have a knot, you take a branch double cover, then it is a rational homology sphere. It is a very classical approach. So if your knot is smoothly sliced, it bounds a disk, and then you can take a branch double cover of B4 branched over your disk. That gives you a rational homology 4-ball smooth, bounding your branch double cover of K. Which means that if you can obstruct the existence of a smooth rational homology 4-ball bounding your branch double cover, then automatically you prove that your knot is not sliced. And looks very simple, but it is actually a very strong approach. And in fact, the slice ribbon conjecture for two-bridge knots were completely solved in this way. They just obstruct this existence of such a rational homology 4-ball, and that was it. But in this case, in this 2-1 cable of figure 8 case, the problem is that this doesn't work. Reason is such a 4-manifold does exist. In order to see why it exists, it follows very easily from the Montesinos trick. It's not just for a figure 8. So for any knot, if you take a 2-1 cable of figure 8 and take its branch double cover, then you can represent it as a +1 surgery along its double. So branch double cover of K21 is the +1 surgery along K connects to K reverse. By reverse, I mean you're only flipping the orientation on your knot. Then this, and because the figure 8 knot is reversible and negative amphichiral, this figure 8 connects and figure 8 reverse bounds a disk inside the 4-ball. And then you can extend this +1 surgery operation into 4-ball, which gives you a contractible smooth 4-manifold bounding your branch double cover. So here's a schematic what's happening. So here's your K and K reverse, and you have a +1 surgery. What happens if you do a quotient along this strong, the canonical strong inversion of this knot is that your ambient space becomes S3, but then the fixed point set is kind of looks like this, and then they're connected by going along this axis, which becomes a 2-1 cable. So what we have learned from this failure is that it is not enough to simply look at whether your branch double cover bounds a smooth rational homology 4-ball. We're lacking information, which is asymmetry. So we're gonna use the deck transformation, which comes naturally from the deck transformation operation. Okay, so here's a slightly more improved approach. So instead of just requiring that you don't have a smooth rational homology 4-ball, which fails because it does exist, now we require that for any smooth rational homology 4-ball bounding your branch double cover, you have a deck transformation tau on the boundary, but it is very unclear why it has to extend smoothly to the interior. So if it always doesn't extend, then you're proving that the 2-1 cable is not sliced. So now that looks like a better approach, but it fails anyway. As I said, figure 8 is rationally sliced. So if you take a 2-1 cable of that rational sliced disk, then you get a rational sliced disk of the 2-1 cable, which is very, very nice. So that you can take a branch double cover along of your rational homology 4-ball along it. Then, by doing so, you get a rational homology 4-ball together with the involution, which restricts to the transformation on the boundary, and therefore this approach will fail. Such an extension do exist. So the second try also failed. But what we have learned here is that probably we need better structure. Nice thing is, following the proof of Levine, you see this rational homology four-ball that we have used in our construction is this thing. And that's not spin. It doesn't have a spin structure. So we have to use that anyway. So here's our final form of our obstruction, that we require that your branch double cover does not bound the smooth rational homology four-ball such that the deck transformation of the boundary such that the deck transformation of the boundary extends smoothly to the involution of the interior, and also your interior carries an involution invariant spin structure. So if you can prove that such a thing doesn't exist, then you are proving that your knot is not sliced. So in the case of 2-1 cable, this obstruction was carried out using Heeger floor homology. The idea is that in this Montesino string, this diffeomorphism is so natural that it is equivalent with respect to the deck transformation here and the strong inversion here. Using that, we could just compute everything. The algebraic obstruction is that there is a charge conjugation iota which relies on the fact that there is a spin structure, and then you have a mapping class group action on the Heeger floor homology. So we're going to prove that there's no local 0-degree element in HF minus of the branch double cover such that which is invariant under both iota and tau. If there's no such element, then it is not sliced, and this was carried out by computing everything. You compute the Heeger floor homology, you compute iota, and you also compute tau, which can be computed from here in the HFK side, and then you do a Large-Surgery formula. Okay, so that was only the 2-1 cable case, which is not today's topic. So the reason that this seemingly wonderful approach cannot be used in the higher cable case is that things are not computable anymore. We are relying on this this central fact that if you take a branch double cover of 2-1 cable, then it is realized as a surgery of a very simple knot. It is not true anymore if you take a higher cable of the figure 8. So if you don't even know what your manifold is, obviously you cannot compute your Heeger floor homology. So we need a new idea, and which comes from the observation of Aceto, Castro, Miller, Park, and Stifsich, who came up with a very much easier proof of the 2-1 cable being not sliced, just adapted to the figure 8 case. Their observation was that in this two copies of CP2, there is a smooth concordance from the torus knot T2n, 1 minus 20n to 2n, 1 cable figure 8 of homology class 2n, 6n. So if you assume that this is sliced, then you can cap up with a hypothetical slice this to get a slicing of this torus knot inside 2CP2 with a prescribed homology class. And this observation relies on this untwisting of figure 8 using two untwist circles. So here's a figure 8 knot, and then you isotope in this form, and then you add -1 full twist here and there, then magically it becomes an unknot. The price you pay is that you don't have the frame is not ciphered framing anymore. After twisting, it becomes a minus 10 framing. So if you cable it, the cable 2n, 1 cable of this is not unknot anymore. That's why this torus knot appears here, because it has a minus 10 frame. And this magical process actually comes from one of the old works of William Bollinger in his paper about configuration of spheres in NCP2s. So what he observes is that if you take a twist knot like this, And then if you add if you twist here, then this crossings get reversed, and therefore you can reduce this twisting number by 1/2. So what's happening here is is that here you're starting with this kind of clasp. And then you isotope this into this position. And then you add a twisting here. Oh. Then you're adding a -1 full twist here. So it becomes something like this. And as you can see, you can just simply isotope it. So for example, this becomes this. And this becomes this. Okay, and then this is nothing but the same class, but intersection is reversed. So you can isotope it back. The price you pay is that the number of half twists there gets reduced. Okay, so here it is nice, but then this has a linking number with the knot, which is 1 if your number of twists is even, and sorry, it's not 4. It's 3 if your number is odd, and that's how you get these twistings. One of them has linking number 1, and the other has linking number 3. Okay, so as a result, we get a 2n,1 cable of your surface, which is a smooth concordance. Yes, sorry. Smooth slice disk inside a 2CP2 of homology class 2n,6 and bounding, not cable figure 8, but bounding this torus knot. Okay, so we have to do some branch cyclic covering to make things spin. The homology class is 2n,6n. So in order to achieve an invariant spin structure, we have to take a branch cyclic cover where the order is a power of 2, maximally. So what you're saying is that you write 2n as a 2 to the power of k times m, where m is an odd integer, and then you take a branch 2k to the power of k-fold cover, and you take SW, and then it has a deck transformation, which is 2 z modulo z mod 2k full symmetry of your branch cyclic cover. Okay. Then you can, since this is a maximal power of 2 dividing your homology class, you can see that there is a unique deck transformation invariant spin structure. We call it S0. Okay, so we have a spin structure. It is invariant under deck transformation, which makes it a perfect setting for applying Seiberg-Witten theory, real Seiberg-Witten theory. So we start by defining the higher kappa invariant, or higher real kappa invariant, as which Masaki also mentioned in his talk. So this kappa, this real kappa invariant of order k, is nothing but the real kappa invariant for the branch cyclic cover. Okay, so branch cyclic cover with a unique invariant spin structure, but then instead of taking the whole deck transformation group, we only consider its 2 to the power of k minus 1 fold power, so that it is an order 2 symmetry. So it is nothing but, so in other words, this is nothing but this following thing. So you have a k inside S3. By taking 2 to the power of k plus 1 fold cover, you get a sigma to k minus 1 of k. And then you have a pre-image of this knot under this covering map, which is a knot, which we call it k tilde. Then this is another way of saying that you're taking this real kappa invariant of this manifold and this pre-image knot, k tilde. And this takes values in rationals, and more precisely, they're integers over 16. As I said, we're going to apply something called the real 10 over 8 inequality, which was first proven by Kono, Miyazawa, and Taniguchi a few years ago. And here's their statement. If you have a smooth concordance between two knots in S3 inside some twice punctured smooth four manifold X with B1 equal to 0, and let's suppose that you have this homology class of your concordance satisfy this relation so that you can take 2 to the power of k fold branched cover to get an invariant spin structure. Then you have this inequality. So you take a B plus of 2k fold cover, you subtract the B plus of the 2 to the power of k minus 1th cover, and then there's a difference of kappa invariance. It is bigger than or equal to minus signature divided by 16, and then there's an extra term here. In general case, the extra term doesn't exist, so alpha equals 0. But in a very special case where the k, the incoming boundary k is k strongly spherical, which I'll define in the next slide, and this term is bigger than this, then you can take alpha to be 1. So the inequality becomes sharp. Okay, so what does this k strongly spherical knots mean? They are knots with the simplest possible real Seiberg-Witten floor spectrum. So here's the definition. So we say that a knot is k strongly spherical for some positive integer k if this higher as the real Seiberg-Witten floor spectrum, which is just defined, is another way of saying this, is nothing but some complex sphere. So so this dimension of your complex sphere is nothing but minus kappa invariant. So it just says that SWFR is determined only by this single number kappa invariant. And it also has a property that this value is also equal to the Froishoff invariant, which is actually a very crucial observation. Okay, so how many are there knots? So surprisingly, the torus knots of this form, so the even torus knot where the even part is 2 to the power of k times odd number, then the first step of our proof is that this torus knot is actually k strongly spherical. So under the lens of this real Seiberg-Witten theory, torus knot just looks like L spaces, which is very weird because torus knots are very far from being alternating knots or L spaces. But anyway, somehow this is true. The idea is we use the correspondence of Mruvka, Oshvat, and Yu, which identifies the irreducible solutions, irreducible critical points with solutions of vortex equations. So the setting is as follows. You're given a Seibert rational homology 3-sphere, fibered over sphere, and then you're looking at the canonical spin C structure on Y and assuming that it is self-conjugate, which is our case. Then, after treating a very nice metric, and then the irreducible critical points of this Chern-Simons Dirac functional for this spin C structure corresponds to these elements, which I'm not going to explain in detail because I'm not a gauge theory expert. I'm not certified to explain the detailed things. I'm sorry. But anyway, the really important part here is that we're looking at the action of j tau on this thing. J, this is kind of holomorphic orbifold divisors, and this is kind of anti-holomorphic orbifold divisors. And J swaps these elements. So if we can also prove that J tau also swaps C plus and C minus, then it'll mean that if you take the fixed point spectrum, then all these irreducible critical points go away, and therefore we're only left with this complex, or the reducible solution, which contributes to its complex sphere. Okay, so we have to show that tau preserves them, and then it will automatically follow that J tau swaps them. And the sufficient condition for this to happen is that on the complex 1 orbifold given by the base orbifold of Seiberg vibration, the induced action of tau has to be holomorphic. If that's true, then it'll preserve the C plus and C minus separately, and the proof will be done. In order to prove that, we have to understand the deck transformation on the cyclic branch cover very, very well. Okay, so we work over this very general setting of 2k times odd, comma q. Q is also an odd number, so its branch cyclic cover is nothing but this Britzkorn sphere, Britzkorn rational homology sphere, 2k times 2k comma 2k m comma q. Then these things always have this kind of plumbing graph. You have a one leg which corresponds to singular fiber whose order is q. Order is m or q, one of them, sorry. And then you have other singular fibers, 2 to the power of k of them, which are identical to each other. So it's like a octopus, like if k is 3. Since you're seeing 2 to the power of k identical legs, you can just easily predict that the Plum 4 manifold can also be realized at 2 to the power k fold symmetry, and that on the boundary that will be the deck transformation on the branch cyclic cover. And that is actually the case, but the proof is not entirely obvious. To prove it, we turn it into a surgery diagram. We're only looking at the boundary, so it's much better. We first construct the 2 to the power of k fold symmetry on the 4 manifold. On the boundary, it looks like this. You have a central surgery circle, which corresponds to the invariant leg. Then you have 2 to the power of k surgery circles which look the same, and which are cyclically permuted by our z mod 2 to the power of k action. So if you take a quotient, it just becomes like this. And here is the branching locus. So if you only look at the ambient space, it just has three surgery circles like this. And you can simply see that this is a surgery of coefficient 1 over n over n naught, and therefore is simply S3. And then you can also show that under this identification, your knot is the desired torus knot. There can be a better way, but we did some overkill, showing that they have all identical surgeries, and showing that large enough slope is a characterizing slope for torus knots. Okay. Now you're taking the S1 quotient, and then you can easily read off what the action on the quotient should be. It turns out the action is just as what you would expect. It acts linearly in this region where you have a cone point of order 2 to the power of k times m. Then you have identical cone points, 2 to the power of k of them, which are cyclically permuted. This is obviously holomorphic because it's holomorphic here and it's a linear action here. And it follows that since tau action is holomorphic, the real Seiberg-Witten spectrum is spherical, is a complex sphere, and by definition, torus knots are strongly spherical. Okay, that is nice. That is really nice. But it doesn't tell you anything about what is the value of the kappa invariant. It just tells you that your spectrum looks very nice. So in order to compute this thing, we have to compute it in a very different way. And that's where our argument in our previous paper, when we proved this non-sliceness of 4n plus 2 comma 1 cables, come in. There, what you do is that we use the Dai-Sasahira-Stofrigan lattice homotopy type and change it into O2 symmetry, O2 symmetry setting, and then apply Sullivan conjecture. For that, we have to start again from this z to the power of k fold symmetry on the Plum 4 manifold, which cyclically permutes all of them. Okay. So let's look at the lattice floor spectrum of this manifold, which in general will look like this. And this picture is, I just grabbed it from Dai-Sasahira-Stofrigan paper. None of them are here, but thanks. So this spectrum has a prescribed O2 action, where O2 is a S1 together with a J tau. And J acts like this. It acts by flipping the left side and the right side. And the J tau action also acts in the same way. J tau also flips the left side and the right side, and therefore its fixed point set is nothing but the central sphere, which is a complex sphere because central sphere is a quaternionic sphere. So, but that is not exactly the Seiberg-Witten floor spectrum. Well, I would say we don't know yet, because what we just have is an O2 equivariant map from this combinatorial space to the Seiberg-Witten spectrum. And we only know that it is O2 equivariant and is a non-equivariantly homotopy equivalence. Well, you can also prove that it is a S1 equivariant homotopy equivalence, but it's not really needed here because we're going to observe that the domain and codomain are finite O2 spectra. And therefore, by Sullivan conjecture, it will induce a Z isomorphism of Z2 coefficient cohomology between the J tau fixed point sets. On the codomain, the fixed point set is nothing but the real Seiberg-Witten spectrum. In the domain, the fixed point set, as you can see here, is a complex sphere of dimension exactly 1/2 of the Neumann-Zibben invariant. And it induces an isomorphism cohomology, which proves that this dimension is exactly the half of the Froishoff invariant, which is the kappa invariant, because your spectrum is spherical. Therefore, we deduce that the higher kappa invariant is exactly minus 1/2 of the Neumann-Zibben invariant. Okay, so now we're in a very nice state, because now you can compute everything combinatorially, every term arising in the 10/8 inequality. Let's go back to the plumbing graph, but now adapt it to our actual case, in which case your plumbing graph looks like this. It's an octopus with bigger leg and smaller head. And in order to compute this mu bar invariant, you have to know where the spherical Wu class is supported. It is supported exactly here, the central node, and half of these nodes. So Wu square is exactly this. But then this plumbing graph is negative definite, and there are these amount of nodes. And the mu bar is, by definition, sigma minus the Wu square divided by 8. It follows that it is minus 2 to the power of k minus 1/4, and therefore kappa is half of that, which is very surprising because it doesn't depend on m. It's just depends on k, and it's very clean. Okay, we have much more quantities to compute. I'm not going to show how I'm going to compute it because it's very messy. But so for B plus and signature, we're going to use this lemma, which basically follows from the G signature theorem, that they can be computed using these terms. And here the difficult to compute term is the sigma n, which by definition is the sum of Levin-Tristram signatures. But our knot is a torus knot. Then the Levin-Tristram signature can be computed by counting some points. And if you count it very well, then you realize this has a very nice form. And using this formula, you can now compute all these terms. The B plus of 2k fold cover is 2k plus 1. The next term is 2 to the power of k minus 1 plus 1. And the signature is exactly 2, always. It doesn't depend on m, again, it just depends on k in a very nice way. Now let's try to plug into our inequality. It becomes this, and we have alpha equals 1 because our knots are strongly spherical, and b plus here, this is bigger than this. Okay, so let's look at the inequality, and magically, everything black cancels out. And somehow they always perfectly cancel out, and therefore the inequality you get is 1/2 is bigger than or less than or equal to 0, which is obviously a contradiction, unless you're living in a weird world. And and therefore we've arrived at our conclusion that even cable of figure 8 is always smoothly sliced, and always not smoothly sliced. And then you can also prove much stronger statement. Namely that if you take a negative minus c copies of these cables and take a connected sum, then their real kappa invariant is also non-zero. The proof is basically the same, the 10/8 inequality, which shows that it has infinite concordance order, which is the statement that we wanted to prove. Okay, so we arrived at our conclusion, which is very nice, but when we were writing this paper, the one that puzzled us is the cancellation here is too miraculous. So we took one concordance inside 2CP2. We take a lot of cabling. We took a cyclic branch cover. But in any case, all terms in the 10/8 inequality just cancel out. So we thought it might be coming from some geometric property of the smooth concordance itself from here to here. And we don't know exactly what it is, but we think it might make proof even cleaner and probably make it apply for other knots as well. Okay, so now that smooth sliceness of cables of figure 8 is completely done, but there's still some remaining questions about this figure 8. So first of all is, what is their smooth slice genus? Intuitively, you might think this is slice genus of figure 8 times the cabling parameter, so it might be n. But interestingly, Jong-Wan Park once told me that there is a smooth genus 1 surface bounding a 2-1 cable. So that's not always the case. So here's the question. Is there any cabling parameter n such that n,1 cable has smooth genus at least 2? This was one of the questions that I was trying to ask from 2020, and then we still don't know what is the answer. If any of them has bigger than 1 smooth slice genus, then it will be very cool. And then there are some other questions like, are they topologically sliced? Or what if we change figure 8 into other negative amphichiral knots, which is necessary to rule out all the Miyazaki examples? And then since we're just proving this non-sliceness by 10/8 inequality, we have nothing to say about their linear independence, so you can also ask them as well. And thank you very much. Thank you.